What if robots had the fluid intelligence of a foundation model? Today, we break down a major CVPR highlight, the SaPaVe paper, a breakthrough in vision language action models for autonomous robotics. Active perception is the link between seeing and doing. Let's see how this architecture works. Moving from simple observation to goal-oriented manipulation, this is the future of robotics. Starting the full breakdown right now.
On the left, a locked head robot reaches blindly and fails. On the right, it pivots its head to look first, then accurately completes the grasp. Most current generalist vision language action models, or VLAs, treat their cameras like static sensors. They are trained almost exclusively on datasets captured from fixed, near-perfect egocentric viewpoints. But a kitchen or a workshop is rarely perfectly arranged. Targets get buried behind other objects, hidden inside cabinets, or sit completely out of view. When a static VLA loses visual contact with its target, the control policy collapses. It lacks the ability to actively search for what is missing. Attempting to forcefully fine-tune a unified VLA to move its head introduces severe, unmapped viewpoint shifts. The physical manipulation pathways simply were not trained to handle a shifting reference frame. This creates a paradox. Moving the camera reveals the target, but doing so actively degrades the model's ability to accurately execute the physical task. To solve this, a robot needs two distinct capabilities. The first is semantic active perception, the ability to purposefully shift the egocentric view to reveal task-critical cues hidden in the environment. The second is active view execution, the inverse ability to take those newly acquired perceptual cues and translate them into robust physical actions, even when the resulting camera angle is suboptimal. Attempting to map both of these capabilities into a single, unified action space causes an immediate architectural conflict. The complex mathematical gradients required for high-dimensional arm kinematics actively interfere with the simpler gradients needed for visual tracking and camera panning. Researchers at Peking University and the Beijing Academy of Artificial Intelligence developed the SaPaVe framework as a systematic solution to this interference gradient. To achieve active manipulation, perception and physical action must be decoupled at the architectural level. The agent needs to perceive purposefully and act meaningfully, without cross-contaminating the data streams. SaPaVe is built on a variant of the diffusion transformer, or DIT, specifically designed for continuous robotic control. The system continuously ingests a stream of multimodal embeddings, including RGB images, depth maps, and textual instructions. These embeddings pass through alternating self-attention and cross-attention blocks to establish temporal dependencies. The core innovation happens at the decoding stage, where the latent vector is explicitly split into two separate pathways. Rather than forcing the network to output a single, monolithic action chunk for the entire robot, one multi-layer perceptron decoder is dedicated exclusively to the 2 degrees of freedom head camera. A completely separate multi-layer perceptron governs the 26 degrees of freedom across the dual arms and hands. This division of labor isolates the learning gradients. It prevents the massive, complex math required to move a 26-joint body from overwhelming the relatively simple logic of panning a camera. By architecturally decoupling the action space, SaPaVe isolates the mathematical optimization, ensuring the robot's hands do not confuse its eyes. With the architecture in place, the system undergoes a bottom-up, 2-stage training strategy. An embodied agent must first learn how to look before it learns how to touch. Stage 1 entirely isolates the semantic camera control mechanisms. The researchers use a dataset called ActiveViewPose 200K to teach the model embodiment-agnostic camera movements based solely on semantic instructions. To process this data, SaPaVe utilizes a parameter-efficient vision-language adapter. Think of it as a small matrix that locks onto the side of the pre-trained vision-language model. This low-rank adaptation matrix injects task-oriented camera movement priors directly into the system, filtering the data stream while leaving the original weights completely untouched. Stage 1 successfully bridges internet-scale visual knowledge with robot-scale camera control, utilizing less than 2% of the model's total trainable parameters. Now the robot knows where to look, but as it actively moves its head, it destroys standard 2-dimensional spatial priors. A constantly shifting egocentric reference frame completely destabilizes the kinematic coordinate accuracy the robot requires for precise grasping. The solution is universal spatial knowledge injection. This forces the model to understand the room using three-dimensional geometry, rather than relying on a flat pixel space. This mechanism incorporates arbitrary geometric modalities, specifically mapping the absolute depth of the scene. Simultaneously, it processes the camera's intrinsic parameters alongside that incoming depth data. All of this spatial data is routed through the Map Anything Foundation model encoder, allowing the system to seamlessly blend visual and geometric modalities. By explicitly injecting 3D spatial priors, the DIT maintains absolute spatial precision for its end effectors. As a result, the physical body becomes completely immune to the dynamic perturbations caused by the active head camera. To test this architecture, the researchers introduced ActiveManip-Bench, a rigorous testing suite designed specifically to measure visual complexity and out-of-view manipulation. The testing parameters move past atomic fully visible skills, focusing instead on occluded scenarios that strictly require active semantic exploration to solve. In real-world fetch from tasks, the behavior is clear. When faced with occlusion, Agent actively maneuvers its head downward to peer inside the drawer, establishing a visual lock before the arm attempts a grasp. This architecture also generates a critical byproduct, closed-loop recovery. If a target object is manually moved out of frame midway through a task, the active perception pipeline instantly overrides the physical body, initiating a new search protocol to reacquire the target. The robot is no longer executing blind, pre-calculated trajectories. Its perception and its actions are continuously informing each other in real time. This chart illustrates the quantitative performance of the decoupled SaPaVe architecture against state-of-the-art generalist baselines on the active manipulation benchmark. Looking at models like Pi0 and GR00TN1, their static camera constraints trap them in the 40 to 50% success range when confronted with complex, occluded tasks. SaPaVe breaks out of that bottleneck, achieving a 75.2% average success rate across the exact same scenarios. In physical deployments, the delta grows even wider. SaPaVe achieves up to a 31.25% higher success rate in real-world hardware tests compared to unified action space models. These results demonstrate that merely scaling generalist VLA models with more data cannot solve the physical challenges of occlusion and dynamic viewpoints. Robust physical interaction in unpredictable environments requires the strict decoupling of perception from action, bridged only by rigorous 3D spatial priors.
SaPaVe is more than just an architectural tweak. It's a paradigm shift, moving VLA models from static observation to active, purposeful perception. By coupling semantic instruction with dynamic execution, it achieves an 85% success rate in the real world, outperforming state-of-the-art baselines by up to 40%. This is the infrastructure for 2026's agents, solving the visual bottleneck to build truly autonomous general-purpose robotics. If you found this breakdown valuable, like and subscribe for more high-signal AI research. Check the newsletter link in the description for the full deep dive. See you next time.